anatomists and physiologists. This video is another video in our endocrine series. This time we're talking about endocrine glands, and we're just finishing up our conversation. We already talked about the hypothalamus and all of the things around there, but now we'll just wrap it up with the rest of them. So we'll start by talking about the thyroid. The thyroid gland is located around the trachea, that's this blue thing here, or your windpipe is another name for it, and it's below the larynx, which is your voice box. And there's a skinny bit of the thyroid that connects both sides, and then those sides of the thyroid are thicker. The thyroid looks bumpy, but if we were to look at it, like on a microscope, we'd actually see that it's just a bunch of hollow follicles. And we have like this epithelial layer here, and then inside there's stuff. And inside is called colloid. So highlight that in yellow. Colloid is what's inside, and inside with colloid is a bunch of iodine, and there's a glycoprotein in there. Glyco means sugar, protein means protein. It's like a sugary protein with iodine in there. Okay, so thyroid hormone is actually two hormones. So thyroid hormone it actually is T4 and T3. And the number 4 and the number 3 refer to how many atoms are on there. TH, thyroid hormone, acts on almost every cell. It can directly enter a cell and cause protein synthesis. So it's a steroid-based type of situation. So some of its effects are, here's some of its effects are increasing metabolism and also heat, because if they increase metabolism, we're also increasing heat. We can also regulate tissue growth. And development at the proper times. At the proper time, that's the important qualifier there. And then we can also maintain our blood pressure. So there's lots and lots of things. The cool thing about thyroid hormone is that we can store it a while until it's needed. So it kind of can just like hang out inside this colloid space. And then when TSH from the anterior pituitary is secreted, that's when the stored thyroid hormone is released. So remember that the anterior pituitary, let's see, we have anterior pituitary releases TSH, thyroid stimulating hormone. Then that promotes the thyroid to release TH, thyroid hormone. And TH is normally released in the form of T4, and then we use it in the cells as T3. So we just kind of rip off one of the iodine molecule or iodine atoms. So I've given you an example of like what thyroid hormone does, but there's so many effects. So here's some examples. This is a table from your text on the many, many effects that thyroid hormone has on target tissues. So mostly the thyroid is making T4, but we're using T3. So somewhere along the way, one of those iodine atoms is removed from T4 to make T3, which is usually what we use. The thyroid can cause lots of metabolic disturbances if it's under or over secreted. The thyroid is like super important. So this leads to lots of ways that the thyroid can do us wrong. One example is a disorder called myxedema. And this is a hypothyroid situation. Hypothyroid, which means that there's less TH happening, less than what we need. And this can lead to feel like low metabolism, feeling really cold, constipation, dry skin, puffy eyes, feeling lethargic, edema, all of these things. And it can result in a goiter. So a goiter is when there's an enlarged and protruding thyroid. And your textbook has a picture of it as an example. Um, but this can happen if like iodine is missing. Iodine is in that colloid inside of the thyroid follicles. And the iodine, that's really important for making the functional form of the hormone. So sometimes iodine supplements can help. Another thing that can go wrong is congenital hypothyroidism. So this is a hypothyroidism, so that means still thyroid hormone is less than what we desire. And that happens when the thyroid doesn't develop well. And so this is something we usually test for in infancy, and it can be treated with an oral thyroid hormone in thyroid hormone replacement therapy. On the flip side of hyperthyroidism is most commonly Graves' disease. So this is hyper. Which means that there's too much TH. And this is an autoimmune disorder, so that means that the immune system is causing this. What happens is that the thyroid follicle cells, they're being attacked. But through a series of steps, this actually triggers more thyroid hormone release. And this can lead to lots of metabolism, sweating, nervousness, weight loss. There's lots of stuff that can happen here. And it can be treated with removing the thyroid or radioactive iodine can be ingested, which sounds scary, but it acts on and destroys those thyroid cells because the iodine is what's acting there. So we talked about the thyroid and in our histology image here. We talked about those thyroid follicles. What we didn't talk about yet are these guys, which are parafollicular cells. Parafollicular cells release this thing, calcitonin. Calcitonin. What calcitonin does is responds to high blood calcium released if high blood calcium. If calcium in the blood is too high, we need to put that calcium somewhere. So normally what happens is that promotes bone deposition. So more bone making because we got to put that calcium somewhere. Okay, so the thyroid, this is the anterior view. Now we're looking at the thyroid from the posterior view. So the posterior view, here's our thyroid because it kind of wraps around that trachea, that windpipe. And on the back, we have these little dots here, those little orange guys. Those are called the parathyroid glands. Parathyroid. There's usually about 4, but it can be variable. And they release parathyroid hormone. So parathyroid glands release parathyroid hormone or PTH, parathyroid hormone, which is released when blood calcium is low. Blood calcium is low. Let me show you some of these effects. So here's how PTH works. So in response to hypocalcemia, that's low blood calcium, then we have PTH is released from the parathyroid glands. And it does 3 major things. One is it promotes osteoclasts. Osteoclasts are bone eaters. They're cells in bone tissue that resorb bone and then put that calcium then in the blood. The other thing that happens is that in the kidneys, that calcium is promoted to stay in the blood. So we reabsorb from the kidney tubules calcium, therefore putting more calcium in the blood. The other thing that happens is that we activate vitamin D. Again, this happens in the kidney, which vitamin D is really interesting because vitamin D acts on the small intestine to promote calcium absorption. So again, more calcium in the blood. That's the end goal there. So that's parathyroid hormone, increased blood calcium and secreted when blood calcium is low. The next thing to discuss are the adrenal glands, and the adrenal glands sit on top of the kidneys. So that word adrenal literally means like on top of the kidneys, adrenal. So the renal part, that's the kidney, and then the ad, that's the on top of part. And I kind of think of the adrenals as like if the kidneys were wearing a party hat. Okay, so the adrenal gland consists of three major layers, and it kind of looks like a little triangle party hat thing. So I'm gonna draw it. So it kind of looks like this. So the outside of the adrenal gland is called the capsule. The capsule. Here, I'll zoom in here. The innermost, then there's the cortex, which is the middle part. And then the inner part is called the medulla. And then this guy here is cortex. The cortex has three major layers. So the adrenal cortex, if we were to look, so we have that capsule layer, we have the cortex layer, which is a big guy, and then we have the medulla, the whole insides. The cortex consists of three major layers. So I'll use three different colors of highlighter to highlight this. Okay, so we'll do the outermost layer of the cortex is called, so this whole thing is the cortex. That outermost layer, and there it's all like zones. So this one's called the zona glomerulosa. Zona glomerulosa. And then there's a middle layer, which I'll do in blue. So the middle layer of the cortex is called, again, another zone, zona fasciculata. F-A zona fasciculata. And then the last one, the innermost layer, is like a smaller layer. I'll do in pink. And this one is kind of like the rest of it. The innermost layer. The innermost layer is again another zone. It's called the zona reticularis. So each of those like zones or zonas has its own hormone type it produces. And it all ends, so all of these are cortex. So each of those zonas have their own hormone type or hormone class that they produce. And each of the hormone types that each of these zonas produce all end in this word corticoid. Corticoid referring to the cortex. Okay. So the zona here's I really like this picture from your textbook because it shows like, okay, so here's where the adrenals are, here's a little slice, and then here's some examples of each of those hormones that are secreted. Okay, so for the zona glomerulosa, the hormones that are secreted are called mineral corticoids. That means that they're hormones that regulate the mineral levels in the blood. In the zona fasciculata, these guys are usually glucocorticoids. Gluco referring to glucose, which regulates metabolic stuff, but it deals a lot with blood glucose. And then lastly, the zona reticularis deals a lot with gonadocorticoids. Gonado referring to the gonads, corticoids referring to the cortex. Okay, so let's chat a little bit more about each of these. So the mineral corticoids, when we're talking about those, it's mostly like sodium and potassium are most important. Sodium is most abundant extracellularly, so it really impacts things like blood volume and blood pressure and the levels of other ions. Potassium is also important for membrane potential, so maintaining that proper charge of the cell. A great example of this is the hormone aldosterone. So I'll highlight in yellow, same thing. So the zona glomerulosa is the yellow one in our picture. And so aldosterone, that's the example there. Aldosterone is produced by the adrenal cortex and it acts on the kidneys to regulate sodium absorption for blood volume, blood pressure, and potassium secretion. So that way potassium is eliminated in the urine. We discussed aldosterone in the cardiovascular system as one of those ways to control blood pressure in the long term. And that's part of the renin, angiotensin, aldosterone system to raise blood pressure. So let's take a peek at that. This is an image from our textbook about the different ways that aldosterone can work. And the triggers are really variable. So let's take a peek. One of the things, these are primary regulators. One of the things that can happen is that if blood pressure falls, that triggers the renin, angiotensin, aldosterone system, which we've talked about. So if blood pressure is too low, that will promote aldosterone release, and then that promotes blood volume and blood pressure and all the things. But also, if potassium gets too high in the plasma, or if so that will also release aldosterone. If there's feelings of stress to the body, then the hypothalamus releases this hormone CRH. That's corticotropin releasing hormone. That means it's acting on the adrenal cortex. And thus the anterior pituitary releases adrenocorticotropic hormone, acting on the adrenal cortex. And it's a tropic hormone, which means it's a regulatory hormone. So telling the adrenal cortex to do stuff. So ACTH tells the adrenal cortex to release aldosterone. The benefit of this is that there's more blood volume and then there's more blood pressure to circulate the blood, the nutrients, the oxygen, much better during that stressful thing. Okay, because remember, stress was the trigger there. Lastly is ANP, atrial natriuretic peptide. ANP. And what happens here is that if blood pressure is too high or blood volume is too high, what happens is that this actually inhibits aldosterone release, which means that there's going to be more sodium and more water lost in the urine and leaving the blood, and then it decreases blood volume and blood pressure, which is what we want. Okay, so back to the adrenal cortex. So we have 3 layers of the adrenal cortex. We already talked about the zona glomerulosa. The next one is the zona fasciculata, so we'll talk about that one. We highlighted it in blue last time, so I'll highlight it in blue here. And the zona fasciculata has glucocorticoids. That's its thing. Glucocorticoids. An example of these are cortisol. Cortisol, or hydrocortisone is another name for it, is a steroid hormone. So that means it modifies gene activity. But the thing about glucocorticoids is that they're making sure that blood glucose levels are stable, maintaining blood pressure. And again, cortisol is an example of that. So what happens here is that we have the hypothalamus, because that's the CEO of the endocrine system, right? So the hypothalamus releases CRH, corticotropin releasing hormone. That promotes the anterior pituitary to release ACTH, adrenocorticotropic hormone. And both of those things will lead to then cortisol being released. But once cortisol is released, the cortisol acts on the hypothalamus and on the anterior pituitary gland to say, no, stop. So when cortisol levels rise, CRH and ACTH, they're not really being released. Thus, we're stopping cortisol production and release. And cortisol production is pattern-like. It's high during the morning and it's low as we fall asleep. But stressors can change this. This is one of those instances where the CNS overrides the endocrine system to encourage that release of cortisol. And this can have a ton of effects, but it includes like increasing blood glucose, increasing fatty acids, amino acids, and this is all to promote energy use. So there's lots of stuff happening to make sure that glucose is formed from broken down fats and proteins, but also to make enzymes for things like metabolism. But if we're in times of stress, this is also going to be like the SNS is working, right? And so with cortisol, it actually helps the SNS because we get better at vasoconstricting, which also helps with blood pressure. This is great in times of stress because we're mobilizing the body. But chronically elevated cortisol, like too long for too long, or too high for too long, which can be kind of problematic because we start to work against things like inflammation, immune response, there's less cartilage and bone formation, and we're going to start to interfere with some of those body systems, the cardiovascular system. So there might be like chronically high blood pressure, muscle loss, um, complications with our nervous system, GI function, that kind of thing. Okay, so that's the zona fasciculata, but the zona fasciculata can also release, let me get my red pen here, um, gonadocorticoids. So in your book, it also mentions that the zona fasciculata can also release gonadocorticoids. I'm going to talk about it with the zona reticularis just because that's the example your textbook gives. Okay, so zona reticularis, the androgens. These are a group of hormones, androgens. These are male sex hormones. They're produced in lower amounts compared to the gonads, and we know less about how these guys work. But there's a few things that we do know, is that they promote hair development, in axillary regions and the pubic regions. It also plays a role in sex drive in women And in postmenopausal women, can be where estrogen comes from because those estrogens coming from the ovaries aren't really produced post-menopause. So that's the adrenal cortex. The medulla is a bit less exciting. There's one layer, the medulla, the adrenal medulla, and it produces a group of hormones. That group of hormones are called catecholamines. Catecholamines, we already know what these are. They are epinephrine and norepinephrine. So the cool thing about epi and norepi is that we can break down these words. Okay, so adrenal means above the kidney. Epinephrine also means above the kidney. Epi means above, and neph is one of those words that means kidney, so it means above the kidney. Norepinephrine, slightly different molecule, still above the kidney. A synonym for epinephrine is adrenaline, which adrenaline. You see what I mean? Isn't that cool? Anyways, so epinephrine and norepinephrine, we know them already, but we know them as neurotransmitters. But when they're produced by the adrenal medulla, they act as hormones. But it still is all the stuff, the SNS stuff that we know and love. Their effects can be a bit more sustained and long-lasting because it's an endocrine thing. But still, epinephrine and norepinephrine act still a lot shorter than a lot of other hormones. All right. Here is a table from your textbook to describe and summarize the major effects of each of those adrenal groups we just talked about. So the mineralocorticoids, the glucocorticoids, gonadotropins, and then lastly the catecholamines, the epi and the norepi. You all know me, I like a good one-page summary. Okay, moving on to the pancreas. We're almost there, I promise. So the pancreas is this yellow thing. It's this organ that sits behind the stomach, and it's actually a mixed gland. So the pancreas, it has both exocrine and endocrine functions. Exocrine means that we're secreting something through a duct. Secreting something through a duct, and in this case, it works with the GI tract, specifically the small intestine. We secrete stuff into the small intestine to aid with digestion. And we'll talk more about it when we get there. But the endocrine function means that we secrete on the inside, and this is ductless. So there's no duct there. And this happens in what's called the pancreatic islets. Pancreatic islets. They're also called islets of Langerhans, named after the scientist. And these guys produce pancreatic hormones. So there's two different cell types here. There's alpha cells and there's beta cells. Alpha cells produce glucagon, so I'll highlight that in pink, glucagon, and beta cells produce insulin. Glucagon and insulin work as antagonists, which means their actions oppose each other. Glucagon is released when blood glucose is low. So I'll use my red pen. Blood glucose is low, and insulin is released when blood glucose is high. When glucagon is released, because blood glucose is low, we're going to take actions to raise blood glucose. And this is usually just taking blood glucose or taking glucose out of storage from the liver, usually, and adding it back into the blood, therefore making blood glucose higher. Insulin is released when blood glucose is high, usually after a meal or something like this. Then we want that glucose to go into cells. So once the glucose goes into the cells, then we make it lower. So this is what we're seeing in this image here. This is our balance of homeostasis. So we can see what happens that if blood glucose levels rise, this signals the pancreas to release insulin. Insulin stimulates the formation of glycogen. Glycogen is a glucose storage molecule. So glycogen is glucose storage. And that's where we kind of store glucose until we're ready to use it again. Then what happens is that we also encourage glucose to be used by the cells. And then both of those actions, one storing the glucose and two putting it in the cells, makes blood glucose levels fall. That's great. The flip side is true too. If blood glucose levels fall, this signals the pancreas to release that hormone glucagon, again, released when blood glucose levels are low. So if blood glucose levels are low, we need more blood glucose. So we're going to borrow from our storage. We're going to break down that glucose storage molecule, glycogen. And once that glycogen glucose storage is broken down from the liver, because that's where we store it, then we shove that glucose into the blood, and that brings blood glucose back up where we need it to be. This stimulus is humoral. Notice this, it's coming from the blood, the body fluids, in response to blood glucose levels. There can also be a little bit of a neural stimulus because there's like the SNS layer happening there when we need to like mobilize body systems. The other thing that insulin does is it promotes synthesis of proteins and storage of fats. It promotes glucose uptake into cells because it binds receptors on those target cells and that like ignites glucose being uptaken. When insulin doesn't work properly or it's not there, that's called diabetes. So if insulin doesn't work properly or it's absent, that's diabetes. So type 1 diabetes is when insulin is absent. Type 2 is when insulin's effects don't work. Insulin is ineffective. So either insulin isn't produced properly, it can't bind to the receptors for whatever reason. But regardless, what happens is you get this elevation of blood glucose, especially after a meal, and you can't really do anything about it. So if insulin falls, in cases of diabetes, there's a lot of things that can happen, but it can result in a bunch of stuff. But the things I want you to know about are these three down here. So one of them is called polyuria. Polyuria is lots of urine output. And that's because there's lots of solutes in those kidney tubules, which promotes water leaving the blood. Water leaving the blood gets excreted by the urine. That is a dehydrating thing. Because that's a dehydrating thing, it also makes you super thirsty. That's called polydipsia. So lots and lots of water intake. And then the other thing that can happen is polyphagia, which is being just super hungry. Your cells need that energy, but they don't understand that that glucose is literally right there because insulin isn't available for whatever reason to start the process of glucose entry into a cell. Thus, the proteins and the fat get broken down for energy, and so that stimulates appetite. This can be a problem though, because if we're relying on fatty acid, um, and fats and proteins and things for our primary metabolism. When those fatty acid metabolites rise, they're called ketone bodies. Ketone bodies are acidic, which leads the body getting too acidic, and that's called diabetic ketoacidosis. That's a big word. I'm gonna write it down. So this is the ketone bodies I was talking about. So blood pH goes way down. That's called ketoacidosis. And one of the signs of ketoacidosis is that your breath can smell like acetone. So a little bit like nail polish, remember? That's that molecule. And the other thing that can happen is the way that you're breathing can get a little bit altered because you're trying to like regulate that pH in the body. But so that ketoacidosis, I'll highlight that word. And if untreated, diabetic ketoacidosis can be life-threatening. All right, this is the last one, I promise. Almost the last one, I promise. So we'll talk about the gonads and the placenta. So the female gonads, these are the ovaries, and these guys produce the egg cells. This is where the egg cells come from. They're also called oocytes. Oocytes. But the ovaries also produce estrogens and progesterone. Estrogens, they really work to help mature those reproductive organs, promote those secondary sex characteristics, which are all the things that develop at puberty, like breast development, that kind of thing. But estrogens also contribute to those changing of the uterine lining during the menstrual cycle, how cyclical that is. There's also progesterone, which is a hormone that helps prepare the uterus for that fertilized egg implantation during the menstrual cycle. Again, we'll circle back to this when we get to repro. And then lastly, the testes, those are um, the male gonads, and they live in the scrotum. The testes, they make sperm. Those are the male gametes. And we also synthesize and release that hormone testosterone, which is important for maturation of that male reproductive system and development of secondary sex characteristics during puberty. We'll circle more back to this, and when we get to repro, that's our last unit. Last but not least is the placenta, which is a whole organ formed during pregnancy that has lots of endocrine functions, and it gets delivered after childbirth. So it helps make sure that that fetus is sustained nutrient-wise and all of the things, but it also releases hormones that influence pregnancy. This is stuff like estrogens and progesterone, but also human chorionic gonadotropin, which is HCG, which is the hormone that's detected in the early stages of pregnancy with the pregnancy test. And the same one you can buy like at Target or whatever. And again, we'll talk more about this during the repro unit. I would be remiss if I didn't tell you that the endocrine system is wild because the hormones are produced everywhere. And this slide and the next one are showing you that it's not just the endocrine organs that we just talked about. Each organ in this table produces hormones too. I'm just putting this here just so you know that it's not just the ones we discussed. And even, of course, there are more examples than the ones here and the ones I highlighted in the lecture, but this is just an FYI for you. I'm finally done, I promise. Sorry.